Welcome to Real Vision Crypto. I'm Ash Bennington. Today, I speak with Anders Brownworth, Principal Software Architect at the Federal Reserve Bank of Boston, about an incredibly important topic, CBDCs, central bank digital currencies. Welcome back, Anders.
Thank you very much. Pleasure to be here again.
Anders, it's a great pleasure to have you back. Obviously, an incredibly important topic we're talking about here today. Give us a little bit of the context of who's involved in this, what the structure is, and what you guys are doing.
Yeah, absolutely. So first of all, I have to say that these are all my opinions, not the opinions of the Federal Reserve Bank of Boston or the Federal Reserve in general. So the Federal Reserve Bank of Boston has been working for the past almost 2 years now with MIT on this project where we're building a hypothetical central bank digital currency software code base that allows us to test many different ways of architecting such a system, and really trying to suss out, what's possible, what does current technology allow, what's not possible, and essentially come up with a menu of options of different ways you could build this, and hopefully inform people that are at a much higher pay grade than myself, making decisions about policy and how we should, think about this and how we move forward. So that's what we're doing.
Yeah, this is extraordinarily exciting. I think that people may not realize that there are actually pilot projects right now that are being done, actual code being built, testing some of the ideas, some of the concepts behind what a central bank digital currency might actually look like.
Yeah, I don't think you can really understand something deeply unless you really go and build it. And that's been the guiding principle here. We connected with the Digital Currency Initiative, the DCI, at MIT, and they've already been doing a bunch of thought in this area, and we're very excited about, let's actually boil this down to a code base, and let's really put it through its paces and test it. And I think, that's how you learn. You got to build it.
So let's talk about building it. What are some of the design principles? What are some of the goals? How are you thinking about this at the 50,000 foot level in terms of what the actual sort of, business requirements would be in the business world, but the technological requirements? What does this system need to do to be a success in your view?
Yeah, that's a great question. So to boil it down to one simple word, the answer is fast. Okay, it's got to be quick. So you might look at like all the credit card transactions happening in the world, all of the cash transactions, everything that's happening on SWIFT and ACH, and maybe come up with an idea of like, what do we do now? It's actually kind of hard to figure that out, but you can back into estimates. And, let's just put that at, let's say, 100,000 transactions a second. Let's say that's kind of what it is. And it's in that order. So let's build a system here that tries to reach 100,000 transactions a second and then clear them to finality within 5 seconds. And then there obviously, you have to do that securely. You have to do that scalably, et cetera. So that was basically the goalpost there. Let's try to make this thing, what we'll call fast. So we did that. We put those requirements out there, and then we took several different attempts. Actually, we started with one idea and a way to do that, and we got some numbers. We were able to put some numbers on the board that actually beat those numbers. And then we came to this really interesting point where we had a question. We said, well, why can't we do this differently? And we really pivoted and made a system that, as far as we're aware, probably linearly scales. So we're able to very significantly beat those numbers. So that's what we did. And to be clear, this is a research code base that we're working on here. This is something that is meant to be very flexible and try different things very, very quickly. And it does that. But all it is, at its very core, is a transaction processor. That's all we're really trying to do. We're not trying to answer all the myriad questions around what would surround that, like how do you get into the system, et cetera. But how would you make a transaction processor do that? Now, in order to do that, we had to build some of those things. We'd had to kind of make ways for us to get transactions through the system, et cetera. But we, in a sense, punted on some very critical pieces so that we could concentrate on really making something that was rip-roaring fast.
Yeah, and just to give people a little bit of context on how fast 100,000 transactions per second is, Bitcoin, I think, is around 5 to 10 transactions a second. It's often compared to, for example, credit card processing. Visa, I think, is averaging around 2,000 transactions per second. This is blazing fast.
You know, if you look at a cryptocurrency, let's say Bitcoin, the Bitcoin nodes are very monolithic. They do everything from run the chatty, network where it's moving transactions around the mempool. It's kind of, managing that. It's managing the state. It's checking transactions, and it's a full participant in the network in a single stack. And if you think about it, like a lot of those things can be parallelized. And, why wouldn't you? So if you can parallelize those things and run them across many machines, you can basically break that up into a set of things that can be parallelized and a set that can't. Turns out, really, there's only one thing that can't effectively be parallelized. So we did that. And as it turns out, if you do that and you really, really refine each of those levels, you can reach some pretty impressive numbers. I will add, in order to do this, not only did we have to kind of lower down the list on the, we had speed and we had security. Down lower on the list was like, we need to do this geographically, disparate. We had to have pieces of this system in geographically different places and only consider transactions final when they were replicated across that network. So how do you do all of those things yet do it like blazingly fast? And the answer is you gotta split it up and do the things that you can parallelize, in different layers. So that's what we did.
I mean, the scale of this project is almost astonishing when you think about what the requirements are in terms of speed, in terms of geographic distribution. Really incredibly massive project that you guys are working on right now. Anders, maybe one thing that might be helpful to people, you talk about some of the design sort of structural decisions. Perhaps you might compare it a bit to Bitcoin, just to give someone a baseline for comparison, someone who's familiar with Bitcoin technology. Give us a little bit of a sense of how it compares and how it contrasts with Bitcoin, what you're working on right now.
Well, I think when you're considering a central bank currency, you already have a system of authority, right? Saying that this is a euro or a dollar or whatever it happens to be. So you don't have this situation where you have to come to broad consensus upon whether or not this one transaction has or has not happened. So you can basically say, when you see that transaction, you can say that transaction has happened and that's final. That's never going to be reverted. In the case of Bitcoin, transactions can be reverted. Granted, the farther back on the chain that they are, the less and less likely they are to be reverted, but that is always a possibility. So if you don't have to come to that consensus and you can simply stamp transactions as being complete, then it just lends itself towards doing things in a slightly different way. You can think about something more like a validator, rather than putting it on a network and coming to consensus upon which transactions are considered valid and having to handle things if you do a reorg. In that case, it's different. In the case that if you think about the way you might set up a payment channel and through that payment channel send a lot of different transactions. This is kind of how a lot of traditional messaging systems work. They secure a channel, and then everything in the channel is essentially transactions that happen, and they are not individually secured.
This would be something like Swift would be using this model.
Yeah, that's right. So that's one way to do it. Another way to do it, which is similar to Bitcoin, would be each transaction is essentially an atomic unit. And that transaction is secured on its own. And it doesn't matter what channel it's in. change channels around, it wouldn't matter. Or you could just fire it off a single one, and that transaction would kind of flow through the system. So, clearly we've borrowed a lot of things from the existing cryptocurrency world, Bitcoin in
Right.
particular, for how transactions look and how they work internally in the system. However, we do take some detours where it comes to coming to consensus. For us, it's not consensus of whether or not the transaction has happened. It's consensus to make sure that across all the geographically distributed locations, a majority of them has, permanently recorded that transaction. So that's a little different. That's not to say, however, that, for example, Byzantine fault tolerance might not still be valuable in this case. It can. It really just depends on, how the system is built and how the trust works within the pieces of the system. When you break something out from being a very monolithic thing to kind of having these tiers that I was talking about, it introduces possibilities for you to have to worry about messaging between different layers where you might not worry about that in the Bitcoin case.
Yeah, really interesting. So this is a bit of a semantic question, but do you guys consider the project you're working on now to be a blockchain? Is it a distributed ledger technology? How do you think about what it is that you're building?
Yeah, so it's always going to depend on what the definition of, what do you mean by blockchain, right? In the sense that a blockchain is an ordered list of blocks. Each one contains a set of transactions, et cetera. As it turns out, the first system that we built has something that's like that. However, when people say blockchain technology, they generally mean the entire system, including some kind of a Byzantine fault tolerant capability, and it means many more things than simply the data
Yeah.
structure. And we differ in that case. Now, I did mention that we worked on two different systems, and the first most of what I'm talking about now really does resemble that in some cases. The piece that it doesn't resemble is like, generally you would think of a blockchain as a public data structure that everybody has a copy of. Turns out if you're going 100,000 transactions a second, simply distributing that to everyone is terabytes a day. It's a lot of data. You can't really take that, practically. So it might differ in that way. Then we came. I mentioned we came to this strange kind of point where we asked ourselves a very key question, and that is in the first system that was basically we tried to parallelize everything that we could. The piece that we couldn't, we call the atomizer. And this is a set of machines, essentially a set of machines in a raft cluster that come to a decision on which transaction happened first. Obviously to catch double spends. We don't want double spends to happen. So that forces all those transactions to go through a central point. And it made us ask the question, well, what about not having that requirement? Like if you're in Los Angeles and you buy a hot dog with a bill, a single dollar bill, several dollars or whatever, does it matter that happened at exactly the same time or before or after I did the same thing in New York? Doesn't seem to, right? So if we could release this global transaction ordering bottleneck, we can actually make our system, which was scaling to, I think I have a couple of graphs on this. We had this system that was scaling, the atomizer system that was getting to about 170,000 transactions a second. Once you release that bottleneck, suddenly you can reach, we only tested up to 1.7 million transactions a second, but it's very likely able to scale more than that.
Wow.
So, and also scale linearly. It does depend on the load, the transaction load that comes in. You can't respend exactly the same bill over and over at that rate, but you can spend sets of bills at just dizzying speed.
Yeah, there's so much to talk about here. First, let me give you a chance to define Byzantine fault tolerance. For people who may not know, you are I think one of the world's leading experts in the way that Bitcoin works. Certainly one of the world's leading experts in explaining it to people. I mentioned, I think the last time we were on camera together, that I really, in many ways, started to go down the Bitcoin rabbit hole after watching your visual blockchain, visual Bitcoin walkthrough on YouTube, which is just extraordinary in the way that you've found to communicate this. So let's talk a little bit about Byzantine fault tolerance. What is it, and why is it so significant in the context of Bitcoin?
Yeah, absolutely. So Byzantine fault tolerance, it comes from this idea, the Byzantine generals problem, where you have, let's just say, three different generals running their people, and they're surrounding a city, but they're not sure whether or not the communication between them is compromised or not. Right. So if they all attack at the same time, they're going to win. If any one of them attacks but without the others, they will most certainly lose. So they need this way to be able to coordinate their attacks, what happens at the same time, and that was the general problem. In the case of how this relates to Bitcoin and really distributed computing in general, is we had to come up with a way that we are able to coordinate, a majority of those components to come to agreement on what truth is. And the way that works in a proof of work blockchain, as I tried to highlight in that video, is something like democratic consensus, where
Right.
the messages are passed around with a proof of a certain amount of work that was done on coming to those messages. And we all agree, just the ones that have had the most work behind them are going to be the ones where we'll coalesce. And as long as we get a majority that coalesce around that, everyone else will ultimately follow us. Now, that has been used in Bitcoin and other cryptocurrencies as a way to come to consensus about what transactions have or have not happened. And, as I mentioned, they can be reordered in some cases where, the proof of work behind some might ultimately make another chain more, show more work than the one you might be on. So it is useful there, but it turns out it's actually useful, in a wide variety of areas, not just in cryptocurrencies, really kind of any cases where you want to have multiple disparate implementations come to agreement on what is or is not true. And that might be useful, for example, if you have different types of software, basically different implementations of software agreeing on something happening. So if you had three different implementations and one of them had a bug, the others could effectively just ignore that one and keep moving forward. So there's a lot of implication beyond simply cryptocurrencies, how a system like that might be useful.
So let's talk a little bit about how transactions are secured in this world. I don't know if consensus is the right word, but what is the security mechanism for ensuring that the transactions that appear on the ledger are ultimately valid?
In the case of Bitcoin and other cryptocurrencies, it all comes down to, we all have a collective benefit of knowing which transactions are real. So we follow the hardest chain, the chain that has the most work. In the case of central banks, for example, or any permissioned network, you essentially elect validators that stamp these things, and if you choose to follow them, then simply one of them stamping it is enough to agree that transaction is finalized. And that does give you some ability to really kind of push the speed envelope, where you can have multiple validators going as quickly as they can, yet all able to participate in one system that you have trust in. So yeah, it really depends on where you want to be, where you want to use that. But coming to what is truth is different in these different systems, and really does cause you this interesting ability to question, well, why do we do it this way, and what do we get when we kind of change the assumption set. And that's been
Right.
a very intellectually exciting project with MIT. I have to say, I mean, MIT has been a fantastic partner with us on this, and it's the brightest people in the world, as you probably are aware, and they've thought about this very deeply and at a fundamental level. Exactly why this works, and very, very willing to throw out assumptions, and let's just look at this at the core. Why do we really need this? And let's not just build something the way it was built before because it was built that way before.
Right.
We can just throw that all away and really kind of build from first principles, really. So it's exciting.
Talking of which, how do the individual validators know whether a transaction is in fact valid?
So in the case of the systems that we've implemented, the transactions coming into the system are there are witnesses that have been created that essentially sign the inputs and outputs. I should mention that this system, the first implementation of this, is a UTXO based system. There's essentially tokens, and it works just like Bitcoin. You destroy these tokens and create new ones.
These are the unspent transactions, UTXO.
That's right. So these unspent transactions are allowed to be spent if the private key behind the public key that they're assigned to signs those outputs. And if those signatures are there, then we go through and we stamp the transaction. However, figuring out whether or not those signatures are valid is something you can distribute. In our atomizer setup, the stamping of transactions, you actually don't need to do that as long as you're fed a set of transactions that are already validated. So you can strip that away and have it pass through the system with a lot less weight. So the transactions are, we call them compact transactions. They're really much smaller than the transactions that have first come into the system.
Perhaps you could walk us through what a typical transaction would look like. For example, the coffee purchase metaphor is often used. So if I buy a cup of coffee here at a coffee shop in New York City, what might that transaction look like if you look at the flow through the entire system?
Yeah, great question. So presumably you've got some money, right? So you have some outputs, and some of them have value. Let's just say your coffee costs $5 and you have a $7 bill. I'm saying dollars, it could be any currency. So if your $7 bill, and of course there are no actual $7 bills, right? These tokens can be of any amount. So you come in with 7, you create 2 new outputs, you make a transaction that consumes that 7, and then creates 2 outputs, a 5 to buy the coffee that's sent off to where it should go, and 2 change back to you. And then that transaction, the inputs to that transaction are signed by, you've got the private key presumably, and then you put that out on the network. And when we get it, that's when our clock starts ticking. I mentioned that we have this 5-second window. We actually clear most of these in under 600 milliseconds, but that clock starts for us. Now we got the transaction. We check the signatures, make sure you have validly signed them, because if you're trying to spend somebody else's money, we don't want to do that. So that's part of what we call static checking. There are other static checks we do. We make sure the amount of money going in equals the amount of money going out, because we don't want you to just create $1 million, right? We also don't want you to destroy money. The creation, the minting, and the redemption is obviously a controlled and a special process. So we want to make sure you preserve the money. You don't create any, you don't delete any. Those are static checks. Then this goes on through the system to essentially do the state check. Has this output already been spent? In other words, is this a double spending? Are you using the same $7 to buy a second cup of coffee? We don't want to allow that. So what we do in the atomizer system is we've stripped absolutely everything out of that transaction in the state. The only thing we remember is whether or not that bill has been spent. That's it. We don't remember how much it is. We don't remember anything about it, just whether or not it's spent. The presence of the bill means it is spendable. The absence of the bill means it's not spendable. That's it. So the state is very simple. You can only create, read, and delete. There's no update. So we run that through the state check, essentially. So that's what the atomizer does. It checks to make sure that bill hasn't been spent. And if that one hasn't been spent, and maybe any others that you are spending in this transaction have not been spent, then we consider that valid. And then we stamp that transaction, and then information about that transaction kind of flows through the system, and then you're able to check to see that that transaction succeeded or not. And that's where our clock stops. So we want to do all of that in a very, very tight time frame, and many, many of them per second.
And you're averaging this at 0.6 of a second. Did I hear that correctly?
Well, it's actually the average is a lot less than that, but our tail latency is kind of out there. It depends on how you build this, right? You could just kind of intrinsically feel that if you had all of that state on a single computer, for example, you're going to run into a bottleneck there, right? So depending on how many, we call them shards, these are the machines that share the state, how many shards you have and how much replication there is, and things like that, you can really, really cut that down very, very significantly. In our 2PC system, the other system, the one that scales linearly, that actually, it's even shorter than that.
Anders, I know you have some slides that you wanted to walk us through. Let's take a look at those.
Yeah, absolutely. So this is a graphical representation of the first of the two architectures I was talking about. So this is the architecture we call the atomizer. And you can see at the bottom, transactions come in to the sentinels. You see everything inside the little dotted lines there. That's our system. So transactions come into the sentinels, and you can see there's multiple kind of copies of the sentinels. That means there's many, many, many of them. And we can launch them as needed to handle the load. Those are the things that do that static checking, make sure you're not spending more money than you have, et cetera. And checking signatures, making sure that these funds are actually able to be spent by you. And then you see it breaks out into those three shards, right? That's 1, 2, and n. We could have as many shards as you want. And that's the state. Those things collectively hold the state. And they're actually not singles. They're actually multiple ones of each one of those. But, we don't need to get into that complexity, I suppose. So let's say you had a transaction that spent two different outputs, one that happens to be on shard 1 and one that happens to be on shard 2. So the sentinels will take that transaction and break it up and send one copy to shard 1 and another copy to shard 2. And if they find that those transactions validly, the outputs that they're responsible for validly hold those, that's valid money, they forward it on to the top. You can see the thing that we're calling the atomizer. And the atomizer collects those transactions, essentially sewing them back together. So the two transactions come back to be one. And now it's one, let's just say it's a complete transaction. And the validator is going to stamp it. It's essentially going to include it in the block that it's working on. And it's kind of just running at a block pace that it sets itself, something like a quarter of a second or so. And if that transaction is valid and it stamps it, it sends it off to the archiver, you can see there, and then this thing that we call the watchtower, which is something that the users could query to see whether or not their transaction was successful. Now, the big problem with this, as you see, is all of those lines going into that atomizer, and that atomizer is sort of a single thing. Granted, it's a set of three in the minimum case, 3 different regions running atomizers, but still it's a single choke point. So we were looking at this and we're thinking, you know what, it really doesn't make sense to kind of have that choke point. Can we release that? And so that's when we moved to this alternative architecture, which looks very similar. And as a matter of fact, the transactions look pretty much identical when they come in. We started thinking about this choke point that we have, the atomizer, and it didn't make sense. Could we get around that somehow? So then we moved to this new architecture. This architecture we call the 2PC architecture, or the two-phase commit architecture. And this looks somewhat similar. The transactions, in fact, are identical, and they come in the bottom. You see the same thing. They hit the sentinels, and the sentinels do those static checks just as before. But then it reaches this transaction coordinator level. And there are many, many of these. And when a transaction gets accepted by the transaction coordinator, it's going to go to the shards at the top there that hold the outputs that are in this transaction, and mark them as in the process of being spent. And then when all of them are attested for, then the transaction coordinator, that little coordinator that's doing this, will go to those shards and say, okay, now those are spent. It's also going to say, okay, create the new ones, the new outputs that have just been made. And then when that is done, that falls right back down and the user sees that. You'll notice this is slightly different. It doesn't have that thing we call the archiver and the thing we call the watchtower on the side. And that's because we have a single process that's responsible for that transaction. And we can kind of follow it right through the entire life cycle right there. So that's how the two architectures differ. And it caused us this really interesting question. Do we care whether or not we have a global order for everything? Not saying that we can't come up with a global order of all transactions. We could, but we're not materializing or writing down a global order in real time. Does that matter? It's an interesting question. Does it matter? You might think it matters because that's the way we've done it, but it may not matter.
Yeah, I mean, this is something that's fundamental to Bitcoin, the idea that you have this global ledger of ordered transactions with timestamps, and you can see this. But effectively, what you're saying is, what if we don't need that? What if just being able to verify whether or not the unspent transaction is valid based on the system that you've built, this account-based system, effectively, if you know it's valid, it can be spent. What difference does it make in real time to have that list of ordered transactions if you can construct it later? That's a really interesting technical question.
Yeah, and it's one that I didn't see that coming. I would have thought, well, let's strip it down as much as possible and just make it go as fast as possible. And then we realized that, and we kind of had this. Does it matter in this case, or what about that case? And kind of think through that. Does it matter legally? Does it? What do you really gain from having a materialized list of transactions? This one happened before that. I think that's an open question still. I haven't found a good reason for why that's absolutely required. And it opens up the possibility that maybe there are other things that we're really not thinking about that, we kind of assume we need. Do we, though? It's really kind of interesting when you can dive into it.
I mean, it sounds like you guys are really kind of exploring the first principles of the way that we think about what digital ledger systems do and what's essential, what's not, and how things might be different in a very different use case.
Yeah, and you get to dive pretty deeply. So as I mentioned, these systems are UTXO based, or unspent transaction output based, and that tends to be a more parallelizable way to spend tokens than something that you might see in, like, for example, Ethereum, which is account-based at the lowest layer. If you are trying to do a lot of transactions from a single account, you have to order those because you have to make sure one of them doesn't drain all the money, for example. So that UTXO system might end up being possibly more parallelizable than something that's account based, but it does, of course, depend on the traffic that you put at it. And there's another thing, like, what is normal? What is good testing load here? Is it that we have however many billion accounts and they're all spending at the same time to another completely separate set of a billion accounts? Or are these a relatively low number of accounts? Like, for example, if it's a merchant and they're doing a lot of transactions on a relatively low number of accounts. Like, what does normal traffic look like? That's a research project in its own. And it gets way more complicated if, of course, you were to support programmability and have,
Right.
many other different things aside from just a moving money from A to B.
So maybe it's just another tier or series of tiers that get built to do that.
Could be. That's a great point. You can build an account-based system on top of a UTXO-based system, or you could build a UTXO system on top of an account-based system. That would just be accounts that have a single value that either just gets created or deleted, and that's it. So it doesn't matter. And I should mention, I'm a software engineer. To a software engineer, saying the words token and account, certainly in a cryptocurrency world, mean a very specific thing about how the data is represented at the lowest layers. However, to other parties, token or account, you might say token means no KYC or account means KYC, or know your customer rules would apply. That's a totally different debate. And that's
Right.
actually valuable to suss out, like, what are the language differences here between the different parties that kind of work on this.
Right.
And we really have to come up with a good lexicon that we all agree with before we can move forward. And I would not have guessed that. So, on the token account thing.
Yeah, I mean, this is such an important point. The idea of the way that software engineers think about the world in terms of data structures, lawyers think about the world very differently. And then I imagine there are also people who are thinking about this in terms of social utility. What are the requirements that we need to have a system that a central bank digital currency would foster commerce and inclusivity and all of the things that people who think about things in the sort of more theoretical side of the social and cultural questions about these technologies. I mean, it's just an extraordinary set of complicated and brand new questions that we're starting to wrestle with here as we think about what this might look like.
Yeah, exactly. And knowing what questions need to be asked is part of the problem. We really don't know. In order to equip people to make decisions, you really do have to know what the questions are and then answer them. And what we believe is you have to build it. Yeah, that's the only way you get to the level where you can suss these things out. And it's the only way I've known to figure that out.
So, Anders, we've talked a lot today about the future, about what the future might look like. Give us a sense of what's next as you walk through this process. What are some of the next things that you're thinking about doing? What's the sequence look like?
Yeah, great question. So we're really just at the beginning of this research. We have what we feel is a fast transaction processor. There are many other areas of research that need to be undertaken, and one of the reasons to make this project, we have open sourced this project. One of the
Mm.
reasons to open source it and work with MIT, a great university, is that we can foster wider collaboration around this. So there's working groups that MIT is kind of running. The first one is on privacy and how how that plays into it, because that's a very complex picture right there. There's a lot of brand new things that technology can do, and there's a lot of valid concerns that society has around these things. So figuring out what all the moving parts are there to get the right balance is a difficult problem, and that's part of the research. I mentioned we are looking a little bit at programmability, because that could be a very different set of transaction types. So we're diving into that. We've looked at how programmability sort of works within the system. We're looking at, we've broken it down to 3 different use cases. We're trying to focus very tightly on that and see what that looks like. And there are other areas that need to be discussed, like just off the top of my head, I think offline might be a really rich space to look at, and many others. So we just want to kind of open up the possibility that there are many people here that MIT is trying to coordinate, and there's working groups that you can get involved in. If you go to dci.mit.edu, you can look at the Open CBDC project and see what working groups are out there.
Anders, fascinating conversation here today. You've stretched my brain thinking about these concepts. As we come to the conclusion of this conversation, final thoughts, key takeaways that you'd like to leave our viewers with.
Yeah, this research is very much at its infancy. There's a lot to dig into here. We have really kind of just scratched the surface on really understanding what the right questions are. So there's a lot to do. We think that the right way to do this is in the open. So this is an open source project that you can go and immediately contribute to. We're trying to do our thinking as much as possible in the open and really kind of foster a lot of collaboration, both with other central banks and with just people that are interested in public who have the interest and the skills in this area. And maybe that there's a lot of different directions we could go if we challenge the assumptions of how things might work. If we simply look at what the technology presents to us and allows us to do, that could open something that we didn't really consider, or think about things in a completely different way. I think I mentioned we don't really know what the questions are. The sushi menu at the end of the day of what you can and can't do, and if you turn this dial up, what does it do to that one? That needs to be built, and that's what we're working on building. So my hope is that we get a lot of people contributing to this, and a lot of expertise in many different areas. And MIT is great at kind of coordinating that work and getting it all focused on really learning and achieving something really special. So that's what I would say. Yeah.
Anders, as always, a fascinating deep dive. Thank you so much for joining us.
Absolutely. Thanks for the opportunity. Really appreciate it. It was fun.
Thanks for watching, everyone.
Hey there, revolutionaries. Thank you for tuning in. For more content like this, head over to realvision.com/crypto and get unlimited access to the most brilliant minds in finance and crypto. Join our community of lifelong learners for exclusive access, unparalleled education, and unbiased insights.